Okay, so we have another problem here in our Conquering the Physics GRE book. And it says a satellite of mass little m is in geosynchronous orbit with the Earth, mass m, e, I'm just going to call that big E, such that its orbit has the same period as the Earth's rotation. If the Earth has an angular rotational velocity omega, what is the radius of the synchronous orbit? So, a few things. Let's just draw a rough picture. Probably butchered how you pronounce that, but that's okay. I can do the physics, and I guess that's all that matters. We'll do this blue for the Earth. I mean, we don't... Do we have like a gray? I don't know. Yeah, this works. We'll do this. I don't think it was the moon. It was just a satellite, right? Oh, yeah. It was a satellite. Okay, we can just do it black then. And we'll just do it actually as a little dot. Maybe right here. So this is big M. This is little m. They're separated by a distance r. I'm doing that arrow because we'll work with Newton's law of gravity here in a second. And let me draw this awful orbital. Obviously that doesn't look like the same. Here to here should be the same distance r, but whatever. And we're also assuming it's just going to be going in a circle. So a couple equations that'll be helpful. The first one is Newton's law of gravity. The r hat is just telling us that it's in this direction here. It's just a unit vector. I'm also going to write down some ways we can think of centripetal acceleration, because obviously the satellite we're thinking is going in a circle. We can think of it as v squared divided by the radius. We can think of it as 4 pi squared r divided by the period squared. And we can also think of it as omega squared times r. So these are just equations from our classical mechanics when we talk about an object moving in a circle. I think I've done questions before where you've seen these. I think I actually showed the proof for this. This was the John R. Taylor's solution for one of the problems where you worked with, I don't remember, maybe it was like question 12 or something, but you had to describe the position and the velocity and the centripetal acceleration. So some of this we've actually shown before, and if not, then that's okay. We can, as long as you believe this to be true, we should be all right. Okay, well, the first thing is I'm going to look at these two equations, and I'm going to solve for t. 4 pi squared r equals omega squared r t squared. And the reason I'm doing that is because the problem mentioned that its orbit has the same period as the Earth's rotation. In other words, their t's are the same because that's what the period is. So the period of the Earth is equal to the period of the satellite, however you want to denote that. So let's go ahead and finish this off and solve for t. So the r's drop, and then we divide by omega squared and take the square root. So 4 pi squared over omega squared square root is equal to t. Okay, which you can also think of as being, let's see, the square root of 4 is 2, the square root of pi squared is pi, the square root of omega squared is omega. Either one. So now that we have that, we have an expression for t now. Awesome. And I'm going to go ahead and plug this into here. And we get our acceleration is equal to 4 pi squared r divided by t squared, which will be 4 pi squared over omega squared. And you can probably see how this will simplify to just r omega squared, which, hey, that's the same thing as this. I guess we really didn't need to do that. I'm not sure why I went through this process, but whatever. When you get 1 equals 1, perfect. Anyways, I don't know. I guess I just had a brain lapse and I forgot that we're good. Anyways, so our force due to gravity, or let's just write it like this. The sum of all forces for your mass, that's the satellite, is equal to the mass of the satellite times the centripetal acceleration. And this is from, this is Newton's law of gravity, which we got over here. I'll box that. That is not what I wanted. There we go. So that's going to be big G, which is a constant, big M, little m, over r squared is equal to little m times what? Should just be r omega squared. I mean, we didn't technically do anything wrong over here, but it's not necessary now that I'm looking at it. I don't know what I was thinking. But anyways, you can see the little mass ends up dropping. And then the question was, and let's be consistent, we'll call this big R squared. Actually, we called it little r, so let's just change our big R's to little r's. They're the same R. R squared R. Okay? Just to be consistent with the notation, those radiuses are the same. I didn't want you to be confused if I used a capital R for one and a lowercase r for another. Anyways, you get G big M equals r cubed omega squared by multiplying over by the r squared. If we divide over, you get G big M divided by omega squared is equal to r cubed. And by taking the cubed root of both sides, you get r is equal to the cubed root of gm over omega squared. Or if you prefer, you could write it equivalently like this using exponents. Let's write that g a little nicer. They're both the same. And that is C. Just keep in mind for mine, I just said big M is equal to ME. Right? Yep, that's it. So hopefully that helped. Sorry that I did a little more work than necessary, but regardless, we got the solution, so hopefully that helped.